Yeah, so hello. Today we are going to continue exploring reinforcement learning, and today's main topic will be exploration, and we'll discuss what the exploration in reinforcement learning means, what does it mean to explore the environment, why do we need to do so, and hopefully you'll get some intuition about what is exploitation trade-off, what are the main algorithms for exploration, and all the rest of cool stuff. So let me share the screen. I hope you can see the presentation. Please write something in the chat or tell me. Yeah, so that's great. So today we'll have an unusual kind of webinar in this course. So actually it will be half lecture, half practice session. So I hope there will be not too much material. Nevertheless, it's not very complicated. So I hope you won't have any difficulties understanding it. So first of all, let's outline what we are going to talk about today. First of all, we'll discuss the exploration versus exploitation trade-off in reinforcement learning. It's a very known concept, and there is quite a lot of literature on this topic, and it's kind of essential to understand the problem before we will go on and build some methods to solve this problem. So then we'll look at one application of exploration problem. It's kind of a very concentrated and very simple task called multi-armed bandit. And this multi-armed bandit application, this task, is kind of a testing environment for exploration. So you'll see what it means. And finally, we'll look at some of the mostly used strategies for exploration, starting from heuristic-based approaches, which you've seen before in this course, like greedy strategy, epsilon greedy strategy, softmax, and then we'll go to more theoretically sound, theoretically complicated, theoretically meaningful methods like uncertainty-based sampling and probability matching. So what is exploration? So as it goes from the naming, exploration is connected to the decision whether to explore or stick with the knowledge that we know so far. So in reinforcement learning, we make decisions at each time step. We make decision whether to commit some specific action or whether to make another action. So there is this fundamental choice. If we decide, for example, that we know enough about the situation that we are in, it would be wise to make the best decision from our current perspective. That's called exploitation. So on the other hand, we have exploration. So as it goes from the name, we want to gather more information, and we are not so sure that we have enough to make the decision to do something instead of other things. So the best long-term strategy may involve short-term sacrifices. There is this saying, and essentially it means that our knowledge of the world is imperfect time after time, and in these cases, it would be good to have more exploration to get some intuition about what we don't know so far. So some examples from real life. So first, for example, if we want to go to some restaurant, so first variant is to go to your favorite restaurant that you know you will like, that you know you will enjoy. And Another option is to try something new and hope that you will come across another good variant that probably will be even better that you know so far. So some more engineering examples. First of all, for example, if we work in some software company and we build online banner advertising system. So we have this set of banners and we have the set of users. And at each time, we want to select the banner that we want to show this particular user. So there are several options. For example, we can show the most successful banner that other users like, and probably it will be the safe choice. And the alternative is to show a different advertisement and hope that it will be suitable for this particular user. So there is a bunch of other aspects in this case, like cold start problem, but we won't go into this rabbit hole. So, and the third application, game playing, probably very familiar to you from this course. And in game playing, we make moves, and depending on how sure we are of certain moves, we may want to select moves that we know something about, or we may want to select moves that we don't know anything about, but hope they are good enough. So this is the basic intuition of this problem. So formally, we want to have some kind of a rule based on which we explore or exploit what we know so far. So how do we build these rules? So first of all, let's look into a little bit of theory. So there is this interpretation, this task called multi-armed bandit. So first of all, what is a bandit? A bandit is the set of slot machines in casinos traditionally. And there are several slot machines, and each slot machine has these action that we play this machine, and this machine does some black box magic inside of it and gives us the reward, in this case the money. And either we lose all the money that we have invested in this machine, or we win much more than we have betted. So this is how it works. And from NRL perspective, it is very simple problem. So we have a single state. So there are no transitions between states. And in the state, we have n possible actions. So n is the number of slot machines, and we select only one of them. So n possible actions, and action is which machine we play. So each machine has an unknown probability of success, and the model is that these probabilities are different. So some slot machines are very cheating. They don't bring any rewards hardly ever. And some slot machines are very beneficial. So as a player, you need to select some machine and hope that it is better than the others. So in this environment, the goal is to maximize the total number of successful games. In other words, to maximize the reward we get from these slot machines. And the reward here is either 0 or 1. So it's kind of equal to the number of successful games. So how do we evaluate how good we play those machines? So some theory here. So we have n actions. Each action corresponds to a distinct machine. And for each action, we have the expected reward from this machine. So for some machine, it can be 0.1, 10% games will give money. For some machines, it will be 2%. So in our notation from the previous course, this is equal to the Q function. So expected reward for each machine is the Q value for the corresponding action, right? So those are Q values that correspond to each particular action, each particular machine. So each machine has its own Q value, and it's equal to the average money that we get from this machine. So our task is to find the optimal machine. Our task is to find the A star, the optimal action. And quite understandably, this is the action with the maximum Q value. So it's Q of A star, or V star, or maximized Q value over the actions. So the best machine. So we want to estimate the best machine and play only with it, but we don't know anything at the start. So we'll probably spend some time estimating this quantity. And ideally, we want to spend not too much time estimating this quantity. And how do we estimate how good we are in estimating the quantity? So here, the main metric is called regret. So regret is how much money we lost in comparison to the ideal playing. So there is this ideal scenario that we play from the start, and we know before what to play. So it's unachievable, but we want to be as close to the ideal variant as possible. And this difference between the ideal variant and what we achieved is called regret. And it's V star minus Q of AT, where AT is the machine that we have chosen at this step T. And we want to minimize the total regret. So we sum over all steps that we have done. And for each step, we take the difference between what we've achieved and the ideal. And hopefully, either the difference will be small, that means that we've estimated good machines, or we'll quickly converge to the best machine, and that means that we will know what to do next. So we want to minimize the total regret. This is our main metric. So if you have any questions, please put them in the chat or ask as usual. So this is our main metric, and we want to minimize this regret. And let's see how we can do this. Let's see what strategies we can employ. So in this course, we've already seen exploration strategies. So the first one is epsilon greedy. So I hope this name doesn't surprise you. We've seen it quite often. And epsilon greedy is actually a very simple strategy when we assign some probability for exploration, for example, 5%, and we explore with this probability of 5%, and with probability of 95% with the rest of the probability, actually, we exploit. So this means that at each step we'll have these estimates what is good. They may be imperfect. So with 95% we'll do what we think is better, and with 5% probability we'll do some random stuff. So the advantage of this strategy is that it's quite simple, but it's not particularly good. So we'll see in a few minutes. The next strategy that we've seen is called Boltzmann sampling, and also known as softmax sampling. So in particular, we have Q values, and we sample actions with proportionately to the Q values, probably scaled with some temperature or another constant. So we take our key values, we take softmax over these key values to turn them into probabilities, and then we sample actions according to these probabilities. So actions with greater key values will have higher probabilities and will be selected more often. And the third strategy that we've seen is called decaying epsilon greedy, and it's basically the same as epsilon greedy. The only difference is that we don't have this constant epsilon, but we start with high epsilon, high exploration rate, and then we decrease the exploration rate towards zero. So the intuition is that at the start, we don't know anything about the environment. So we kind of, so there is no difference between exploration and exploitation effectively. Both will be very bad. So hence, it will be better to explore very intensively at the start to get more history, to get more knowledge. And at the end of the training, we'll get much better knowledge about the world. And there will be no need to explore as intensively as before. So we start with high epsilon, and then we decrease epsilon during training towards zero. So it's called decaying epsilon greedy. So let's look a little bit closer to these algorithms and see what is not very ideal about them. So actually, there is one more strategy that I didn't put to this slide. It's called greedy. Well, I didn't put it here because it's actually not an exploration strategy, because it does not explore at all. So in greedy algorithm, we always select actions with the highest values. So we take our Q values and, well, basically we always do what we think is better. It doesn't matter if we know anything about the rest of the actions or not. We always select the argmax. So what do you think will be the total regrets in this algorithm? So will it be high, will it be low? And what are some problems that you think are present in this greedy selection?
It obviously will be high, so we won't pass too far using this strategy.
Yeah, so it will be not zero, it will be very high. And the reason is that it can lock to some suboptimal action forever. So for example, if we are at some intersection and if we go to the left, we get $1. And if we go to the right, we get $1,000. And if we go straight, we get $0. So for example, our agent has visited the left road. And now it knows that if it goes left, it will receive $1. But it does not know anything about the right path. And if it had known about the right path, it would go here, obviously, because there is 1,000 times more here. But it does not explore anymore because it knows that 1 is better than 0, and it basically selects argmax based on the previous experience. So it will always go to the left, and it will always get 1 point. Whereas ideally, we would like the agent to visit the right road and get to know that it's much better. So this is the main problem with greedy algorithm. It does not explore at all, and because of this, the regret will be linear based on the number of steps. So the regret will be 999 for the first step, for the second, for the third, and so on and so forth. So we'll never get to the optimal action. And that is why the regret will be linear. So linear is kind of the worst the worst performance that is possible in terms of exploration for all the reasonable methods. So then we have epsilon greedy. So it's slightly better because it explores. It will not have this problem. It will eventually go to the right and see that on the right side there is much more profit, and it selects suboptimal actions with fixed probability over and over again. So it has some advantages that it will never get stuck in the action that is not optimal, but it also has some disadvantages, also from this fact that it explores forever, because at some point we need to stop exploring because we know everything that we should know. So if, for example, our agent has become a perfect chess player, with epsilon greedy exploration, it will do some stupid things with some fixed probability. And this is not what we want to do. So we want to eventually stop exploring, and the task is to find when we should stop. So epsilon greedy also has linear total regret, and well, that's because with some probability we'll always select random actions, and with this probability we always lose compared to the ideal action. Okay, so any questions on that part, or is it clear why epsilon greedy also has linear regret? Okay. All right. So epsilon greedy is also not very perfect. Let's see what the other algorithms that we know do. So epsilon greedy with decay, it seems like a perfect solution. So first of all, we explore very intensively with the goal that we don't miss anything that we should know. But one major disadvantage is that we need to select the schedule for the epsilon decay. So we want to program kind of the function according to which the epsilon will decrease from high value to the low value. And it turns out that it is very complicated to design the schedule that is both not very slow decaying and both not very high decaying. So if we decay very slowly, it will mean that our chess player will do some stupid stuff for a long time, for a longer time than it should. So at some point it will know the moves, but it will do something strange. And if the decay rate is very high, then it will not explore sufficiently. So it will not explore some parts of the environment that are probably necessary for the agent to learn. And it is kind of the main disadvantage of epsilon greedy with decay method. So if we select the decay rate correctly, the regret will be logarithmic. And it's actually very good. It's as good as most of the algorithms can get. But if we don't select the schedule very effectively, then there will be some problems. So those are the methods that we have seen. So now let's talk about something more theoretically founded, and we'll start with the algorithm called, the family of algorithms called optimism in the face of uncertainty. So if you see the previous if you look at the previous algorithms, it will be obvious that they are kind of not very natural. Because we humans, we don't usually do some random stuff to explore the environment of the life. So we have some prior bias towards some actions or other actions. So for example, which of the following two questions would you like to investigate? Which of the following questions would you like to explore? Whether we can fly if we pull our hair up, or whether the new cafe next to the office serves good breakfast. So which action will you choose for exploration and why? So it's an obvious question, but the trick here is to formalize why we pick the second parent and not the first.
Second can be useful in the future for us.
Yeah, so we may not know the actual prediction how useful it can be. So how useful it is, we don't know it yet. But we have some kind of probability distribution over the usefulness. And as you've said, we think that, well, it's quite likely that the new cafe can serve good breakfast. So it's likely that the reward for this action will be high. Whereas for the first action, we know for sure that it will be stupid to do exploration in this direction because we are very certain that it will not bring us anything good. So it's called optimism in the face of uncertainty. And mathematically, it can be described as the following. So we have some kind of uncertainty corresponding to each action. So for some actions, we have high certainty, low uncertainty. We know for a fact that something will happen or won't happen. And for some other actions, we are not so sure what it will do for us, whether it will be very good or whether it can be a waste of time. But we have some kind of concept that we can take some risk, and if we believe that risk-benefit ratio is good enough, then we'll do some action that we are not sure about. And yeah, we want to try actions if we believe there is a decent chance they are good. So for example, let's move from the domain of people to the domain of RL agents. So let's imagine that we have an agent that has 3 possible actions. And an agent has some kind of knowledge about those actions. So it has a distribution over Q of A1 over the value of action 1. It has also the distribution over the value of action 2 and the value of action 3. So 3 distributions. And those distributions kind of show what the agent expects from these actions. So it expects action 3 to be, well, it knows pretty well what action will bring. But for action 1, the agent does not know anything. But the average is less than action 3. So which action do you think the agent should pick here from those 3?
Maybe it depends on the strategy. In the beginning, we can explore more.
Yeah.
So it can be a red curve, for example. But at the end, we need to go to better and better.
Yeah, so of course it depends on the rate of the exploration. So for example, if we want to explore and we see that for action 1 we know very few things, we may select action 1 kind of to make this curve more well, less flat. So we want the Q value for action 1 to be fairly certain. So it's possible that it will be greater than this green curve here. So we can select action 1, for example. And one strategy for selecting actions is that the more uncertain we are about value, the more important it is to try that action, because it could turn out to be the best action. So it's kind of very intensive exploration. So we always explore the action that we are less certain about. So for example, in this case, we can pick a blue action, and after we have done so, the curve will move to the left. And then it will be quite certain that we don't want to pursue this blue path anymore, because, well, now it's fairly obvious that the green one is uniformly better. So, yeah, that's called optimism in the face of uncertainty. But as you've said very correctly, we actually may not want to select only uncertain outcomes. So if something is very uncertain, but so for example, this blue action here is also quite uncertain. So we don't know whether it will be -2 or +2. So it has higher entropy than the green action here. But nevertheless, we don't want to pick it intuitively. So because we know that even though it's very uncertain, it's very likely that it will be not better than the green one. So here is another rule, another goal that we want to use. So we want to select not only uncertain things, but also with greater expected value. So we kind of want to mix them together. So how do we do this? So let's compute upper confidence bound for each action. So in probability, there is this method of estimating things, which is called confidence intervals. So we can select a confidence interval for each action, for each possible action. And looking at those intervals, we can think, okay, let's always assume optimistic outcome, and let's always take the 95% upper bound. So if the action is good enough and with high uncertainty, then this upper bound will be high. And if the action is with high uncertainty but with low expected value, then this upper bound will be nevertheless lower. So it's, informally speaking, it's kind of assume the best possible outcome for each action, the best possible reasonable outcome, I think. And once we know how to estimate these 95% upper confidence bounds, we should take action with the highest bound. So in this case, in this example, the optimal bounds can be the following. So for blue action, it will be somewhere here, like 4. So for green one, it will be around here. And for red one, it will be around here. So if we want to explore with high rate, and we use these confidence bounds, then we'll explore the red action. And we'll continue exploring the red action until either we know that it is better, or we will know enough of about this action to move this curve to the left. So the idea is to take action with the highest upper confidence bound. So how do we estimate those confidence bounds? So there is this theorem, it's called Hovding's inequality, and it tells that for a given sample of random variable, and a random variable should be bounded in 0, 1. Well, actually, it should be bounded, period. Doesn't matter, 0, 1 or something else. So if it's bounded, for example, 0, 3, we can rescale it to make it bounded to 0, 1. So if we have a random variable which is bounded, then we can estimate the probability that the sample mean deviates from the expectation by some margin with this upper bound.
Distribution should be normal, or we can use any.
So the good thing here is that it works for any distribution which is bounded in 0, 1. So it doesn't matter what is the distribution. The only thing that matters is that the distribution, is that the random variable takes values from 0 to 1 in this interval. So it gives the estimate, the upper bound estimate, that the mean, the sample mean, deviates from the expectation by some margin, u. And you can see that the greater sample that we have, sample size is t. The greater sample we have and the bigger the deviation is, the less the threshold will be. So I don't think that we need to explain how this inequality works. So the only thing that matters here from the practical perspective is that we can estimate probabilities of deviation, and we can use this to compute quantiles of the distribution, and then confidence intervals. So we can apply this inequality for our case. So we want to, we take x and we substitute x with q function, q of a. So q of a is our random variable. And we have a sample of our random variable, q of a. We have the sample. And the sample is the history of our rewards, q with t index. So this is the history of our rewards, and based on our mean rewards, we can compute the upper bound. So here, nt is the number of trials, and p is the probability that we will threshold our confidence interval. So for example, p can be 0.95, and this will correspond to the case when we take 95% upper confidence bound.
Nikolai, am I right that the uncertainty of the action is made from its history? Yeah, somehow.
Yeah, so we have history of actions. So for example, we took action A 10 times, and we track how much reward we got for each of those 10 times. So we have an array of 10 q values for each episode. And this is our sample of the random variable in this case. So this is our qt of a sample. So we take the average of the sample, and based on the average of the sample, we compute the upper confidence bound. So for example, if the sample size is 10, we are not very certain about the average. But if the sample size is 1 million, then probably the Q-value, the actual Q-value, is close to our sample mean. And to estimate how close our sample mean is to the actual Q-value, we use this statistical inequality.
And margin is the difference between the average value and the maximum value from history, yeah?
What do you mean by margin?
UT.
So UT is, well, I think it will be easier to draw this. So we have set of Q values. So Q1, Q2, Q3, Q10. So those are Q values from the history of episodes. And we have the estimate Q hat, which is the average of those 10 QIs. Yeah. So we can estimate the average. So for example, if sample size is 10, then 95% upper confidence bound can be very different from the sample mean. 95% upper confidence bound. So it is equal to Q mean plus, I don't know, 7.5. So it's arbitrary number, just for the sake of illustration. And if sample size is 1000, then upper confidence bound will be something like this. Q mean plus 0.1. Yeah, so is it clear now or not? So the bigger sample size is, the closer upper confidence bound is to sample mean.
And how we select 7 and 0, 1?
And how we select is basically told by Hövding's inequality. So that's actually UT of A. UT of A is in the first case 7.5, and in the second case it's 0.1. So UT of A, so the trick is to estimate UT of A, and it can be estimated by this formula from this theoretical theorem. And the motivation here is that if sample is big enough, if sample size is 1000, then UT of A is low. If sample size is 5, then UT of A is high, because there is high uncertainty and we don't know if Q value is 10 or 20 or 15, so there is high uncertainty.
Can you repeat once again, please? What is NT?
NT is the sample size.
Thanks.
Okay, so that's how we select upper confidence bound. And upper confidence bound is the value that is higher than our Q function in 95% of the cases. So it's kind of 95% quantile for the distribution of Q values. So with fixed probability, we've seen actually what's derived from the Hövding's inequality is corresponding to the fixed probability. For example, in this case, 95% upper confidence bound. So we can estimate upper confidence bound in this fashion. But there is another extension that we can reduce probability during training. So at the beginning, we want to explore very intensively. So in this scenario, probability, in this case, probability will be high. And as we move towards the end of the training, we don't want to explore very much. And we move our upper confidence bound from 95% lower. And it's kind of similar to epsilon greedy with decay. Here we have upper confidence bound with decay. And the thing that is being decayed is the probability, is the quantile of this upper confidence bound. So first we start with 95% threshold, then we take 90% threshold, then we take 80% threshold, and then we move actually to the greedy strategy. So we explore less and less and less and less. So in this case, we can take this schedule where probability is t to the power of, to the degree of -4. And then in this strategy, the upper bound will be given as the following entity: square root of 2 times log t divided by number of actions in the sample. Yeah, so small correction, nt is the sample size not for all actions, but for this particular action. So for this particular action A, sample size. So, and here we have finally the algorithm is called UCB1, and we select action here as argmax of Q of A plus the upper confidence bound square root of 2 log t divided by number of action number that we have took the action A. So it's basically argmax upper confidence bound for these actions Q value. And actually it is quite powerful thing. It's quite good algorithm. It achieves logarithmic total regret. And in comparison to epsilon greedy with decay, we don't need to tune anything here. So we simply take it out of the box and we achieve logarithmic total regret quite straightforwardly. So, sorry. So that's upper confidence bound 1. There is this slight variation called Bayesian upper confidence bound. And I won't go into very much detail about it. If you want to, you can look Bayesian upper confidence bound. Basically, it's similar to the rest of Bayesian statistics. So we assign prior distribution over Q values for each action, and then we use this prior distribution and our data to learn the posterior distribution over Q value for each action. And then we take the Qth percentile of this posterior distribution and select the best action based on this percentile. So the same variant as the same way as in simple Bayesian statistics. So that was kind of the first direction of exploration algorithms. So all of the algorithms that we've seen in this lecture, all of them use upper confidence bounds. So we estimate upper bounds on the utility for each action, and we go where the upper bound is good. So if we have even small reason to believe that something is good, even 5% reason to believe so, we will go there if it's better than the rest. So there is another slightly different perspective on how to select actions, and it's called probability matching. So probability matching is the strategy in which we select action A according to the probability that A is the optimal. So if we look at this picture, how can we explain this probability? So before we looked at the percentiles, at the quantiles. And this means that, for example, for the green distribution here, we looked at relatively this point, 95% quantile. For the blue distribution, we looked at the 95% quantile here, and for the red one here. And if, for example, we did UCB strategy, then we would select the blue line here. Whereas it is not very logical, because the green action is almost always better than the blue one from this plot. And hence, there is another perspective to select actions for exploration. So instead of estimating the upper confidence bound for each action separately, instead of looking how good each action is in the best case scenario, we take the probability that A is the best, then we take the probability that A2 is the best, then we take the probability that A3 is the best, and then we select actions according to this probability. So we can look at these distributions, and so, for example, action A3, the green one, is better than the rest of the two with relatively high probability. Still, there will be some exploration, because action A1 is still better with some small probability, yet not 0-1. So the idea is quite simple. So the trick is, how do we implement this? And the implementation is called Thompson sampling. And basically, let's see how it's done. So first of all, we compute the posterior distribution for each Q value for each action. So those are these distributions here. Green distribution for action A3, red for action A2, and blue for action A1. So remember, those are the distribution for rewards for those actions. So those are the distribution of how reward for each action changes based on the history of our previous episodes. So we compute posterior distribution, or in case of non-Bayesian approach, we simply compute the histogram, or something like the histogram. Then we sample from each action's posterior distribution. So we sample from the green curve. Some point, it can be here, it can be here, it can be close to the mean, and we sample it. Then we sample from the red distribution. It can be higher than the green sample, or it can be lower. Well, most of the times it will be lower than the green sample, but sometimes it will be higher, because this line is still unexplored. And then we sample from the blue action. And we simply compare those three samples, and we select action with the maximum value on the sample. And it will actually select actions proportionately to the probability that this action is optimal. So we can't estimate these probabilities in analytical way, in theoretical way, but we can use Monte Carlo sampling for this purpose. So that's called Thompson sampling. And it's actually also a very powerful algorithm, and it performs relatively similar to the UCB exploration strategy. So, any questions on this part, or is everything clear?
We sample one item from each distribution and compare 3 items, yeah?
Yeah, we compare, well, we sample one item for each action, and we compare for all of the actions. Here for 3 actions.
Thanks.
So let's summarize what we've seen in this small lecture on exploration. So first, we've seen the trade-off between exploration and exploitation. So namely, every time we make an action, we need to choose whether we should select the best action according to our belief, or whether we should explore something else in hope of discovering a hidden gem. So then we've compared exploration strategies. We've introduced a metric for exploration strategies, which is called regret. And regret is basically the difference between the best possible, the best possible action selected from the start and what we've selected from the start actually. And we want to minimize the regret. We want to bring our rewards closer to the ideal trajectory, closer to the ideal action every time. And we want to minimize the total regret, and simple exploration strategies, all of them sometimes fail to do this. So greedy, with very high probability, will have linear total regret because we can never find the optimal action. And epsilon greedy will probably find the optimal action, but it will continue selecting random stuff over and over again until the end of the life. So it also has linear total regret, but the coefficient will be usually smaller. So it's slightly better. Then we saw that epsilon greedy with decay has logarithmic total regret if it is tuned properly, which is not very simple. So finally, we've covered several exploration strategies. First general approach, select uncertain actions. Then we try to select uncertain actions, but with greater expected value. And for that purpose, we used confidence intervals and 95% quantiles. So now we know how to estimate 95% quantiles, and that's called UCB1 algorithm. It is also logarithmic total regret, and we don't need to tune it. So finally, we've seen probability matching approach, and it's slightly different from the UCB perspective in the way that we want to select actions proportionately to the probability that they are the best. So not based on the quantiles, but directly comparing action 1 to action 2 to action 3 and estimating the probabilities that some of them are better. And the implementation of this probability matching, one of implementations called Thompson sampling. And basically it's sampling from the posterior and comparing the samples and making action with the greater sample. So that's it. So if you have any questions on the theoretical part here, I think now is the good time to discuss them.
What is the total regret in the Thompson algorithm?
So I'm not 100% sure, but I'm fairly certain that it is also logarithmic based on the number of steps.
But looks like it has larger variance comparing to the previous algorithm. So it can be better than logarithmic, yeah?
Well, it has larger variance, but as the number of steps increases, so in the limit, variance does not matter, and it will also converge to the logarithmic dependency. So if we make more steps, then each of those distributions will be shrinked. So each of those will be kind of put into the small surrounding of one point. And after it happens, then sampling will not play as much role in introducing variance.
It will be like selecting expectation always, yeah?
Yeah. So it will be like selecting expectation, but also I want to say that it is not very much noisier than estimating quantiles. So if when we estimate quantiles, we also have some kind of variance, because if we have small history, then there will be high variance for quantiles as well. But here, you're right, the variance will be slightly bigger, but I believe it will not play very much role.
Got it, thanks. Can you please explain once again the Boltzmann algorithm from the beginning?
Yeah, sure. So is the same as softmax sampling. So we've seen it several times before, and we've used the name softmax sampling. And so basically the idea is that at current time, we always have some estimates for Q values. So we have estimate for Q of action 1, we have estimate of Q of action 2, and for the rest of the actions as well. So we have these estimates of Qs. And the intuition is that we want to select actions with high Qs. And well, we want to select them more often than the actions with low Q values. And the idea is that we call the softmax function for these Q values. We transform Q values to the probabilities. The higher Q value, the higher the probability. So once we've transformed Q values into probabilities, we can sample from these probabilities. And then what we've sampled will be the action that we've committed. So it's kind of close, it's kind of related to the Thompson sampling in a way that it also samples actions, but it uses much less information. It only uses the mean, the Q, whereas Thompson sampling also uses the whole distribution that we know.
Is it like stimulation annealing algorithm?
Stimulation what, sorry?
Stimulation annealing?
Stimulation annealing. Well, in some way, I think it resembles. But I think that it's kind of more related to Monte Carlo sampling, because we want to estimate this probability that some action is better than the other. And to do so, we don't know how to estimate it theoretically. Instead of this, we estimate it using sampling. And we sample from the posterior distribution that we know at this step.
Sorry, can you show on this plot how Boltzmann works?
Well, yeah. So Boltzmann works in the following way. So it uses only mean Q value. So for this green action, it will be 2.6, I think. For this red action, it will be 2, and for the blue one, it will be 1.4, I think. Yeah, so we have these averages of Q. And that's it. That's the only thing that we have. So we have these averages of Q, and we transform them into probabilities using the softmax function. So after softmax, it will be something like, for the green thing here, probability will be for the green action 60%, for the red action 30%, for the green action 10%. And then we sample actions according to those probabilities. So does it make sense?
I thought we've already sampled when we select the average.
Well, actually not. So let's see a little more thoroughly. So we have some history, yeah. So we have some history, action A1, action A2, blah, 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 action A1. And so that's the history of our episodes, as usual in RL. So for each episode, we have a reward. And we have our current samples of Q value for each action, right? So we have Q1, Q2, Q3. For A0, we have Q1, Q2, and so on. Q55 for A1. And we have only one action for A2. Yeah, only one Q. So what goes on in softmax sampling? So we take those vectors of Q values and we average it, and we average them. So we have Q average for A0, we have Q average for A1, and we have Q average for A2, which is simply the only Q. So we have those Q values. So then we transform them using the softmax function. Softmax. And softmax transforms real values into probabilities. So after softmax, we'll have probability of A0, probability of A1, and probability of A2. And we will select action based on those probabilities. Yeah.
So those probabilities form the new distribution for us, and from this distribution we sample. Yeah.
Yeah, those probabilities form the new multinomial distribution over actions, and from this distribution we sample. Yeah.
Clear. Thank you.
Yeah. So, any more questions that we should discuss now? So I don't think we'll have enough time to work on the practice. But practice this week is quite simple, and actually I was planning to
Maybe at least go through.
Yeah, sure. I was planning to release it as the homework part of this. And as we've only looked at the theory today, I think we can use the whole practice as the homework. So yeah, I'll share the screen now. Yeah, so in this practice, basically the idea is to implement different exploration strategies for simple problem Bernoulli bandit. So there is this class of Bernoulli bandit, which doesn't have a lot of stuff going on inside. And basically it's just the abstract class that uses, that implements some inner workings of the Bernoulli bandit. So first, what we'll be implementing is epsilon greedy agent. So epsilon greedy agent, basically with probability epsilon, we select the random action or we select the best action. So it's what we've covered for a lot of times. So I think I can open it in Colab and write some code for the sake of illustration. So here in epsilon greedy, we have the epsilon parameter, which is the intensity of exploration. So we can get action. So basically, we do something like this here. We sample coin, compare it to epsilon, and if it's less than epsilon, we return the uniform sample. Otherwise, we go to otherwise we iterate over all actions and select the action with the highest rate of successes. Yeah, so Q value here will be success divided over success plus failure for each action. Right? So it's simply counters of successful actions and failed actions for each slot machine. So that's epsilon greedy. The more interesting thing is UCB agent. So UCB is what we've seen in the lecture. It estimates the upper confidence bound. So, and here we already have the upper confidence bound, which is the average, which is the mean of the distribution plus the deviation from the mean at a given confidence level. And here confidence level decays over time. So it's already introduced here. So you simply take this formula and you estimate the upper confidence bounds for each action and select the action with the greatest upper confidence bound. Yeah. So that's UCB. And the final thing here is Thompson sampling. So here the main idea is that here Thompson sampling is done in Bayesian perspective, and we sample from the posterior distribution, which is beta distribution. So I don't want to go into very much detail why here beta distribution is used. So basically, there is a prior distribution, which is beta distribution with parameters 1 and 1. And the posterior distribution for prior beta distribution is also a beta distribution. And the parameters for the posterior are given by the number of successes and the number of failures. So we sample from beta distribution and we compare samples for each action and select the greatest one. So the first thing is to implement these three exploration strategies and then to compare them. So here is a hint, what should they look like in the correct implementation. So epsilon greedy will have the highest regret, and UCB will be better, and Thompson sampling will be even better. So that's the first part. It wasn't supposed to be the part of the homework, but it's, I think, much simpler than the previous homeworks. So I don't think there will be any problems. So
there will be no GPU resources utilization.
Yeah, so first of all, there will be no GPU resources. And secondly, it's much simpler in implementation than Actor-Critic and let alone DQM. So it's much simpler.
Nikolai, by the way, when to expect the checks for these two homeworks?
I'll check the DQN at the end of the week, and depending on when I check DQN, I'll then check Actor-Critic. So the second part is bonus part. So you can do it if you feel like it. You can skip it if you don't want to read more theoretical stuff. So there is another version of the algorithm for the exploration in the Bernoulli bandit, which is called Giddens index. So you can read in the Wikipedia about the Giddens index and implement it in the same variant as those three ones. So the second part will be non-stationary Bernoulli bandit, and here the difference is that in stationary Bernoulli bandit, in the simple Bernoulli bandit, probabilities for each slot machine are fixed. So each slot machine is constant in rewards. So they don't change over time. And in non-stationary, there is one more tweak in the setup, which makes it harder. So each slot machine will be non-stationary. That means that the probability of the reward for the machine will change over time. So some machine, for example, may start with high reward, then go to the low area of reward, then back to the high area of reward, and each of them will oscillate. So it turns out that in this environment, it's also possible to do something at least. And the task is to modify previous agents, or probably make your own exploration strategy that will perform better than UCB in this non-stationary environment. So that's it.
Can you show again the performance comparison of these all algorithms?
So this is for the non-stationary case.
Yeah.
Well, it's basically similar to the stationary case. So the difference is that Thompson sampling works here very close to epsilon greedy, and UCB is not so sensitive. So here you can see that UCB is much worse than Thompson sampling, and here you can see that UCB is much better. So
your agent is Gittins index.
So your agent is not Gittins index. It's basically some modified version of probably UCB or Thompson sampling. So the task is to make another agent which will perform better than UCB. So here UCB performs better than Thompson sampling, and that's interesting. So I think the intuition is that upper bounds are not so sensitive to change in distribution as the samples from the posterior. Because when the distribution changes, so my intuition is that the upper bound will, so the confidence interval will expand, and the upper bound will become high. And this will allow the agent to switch between actions after time. So something like this. And your task is to do better than this. So probably you should make some assumptions that the environment changes. Probably you need to increase the variance. You will need to explore much more. So I'm fairly sure that you'll need to explore much more than in the stationary case. So kind of whatever you want, you can implement.
And what's the deadline?
I'm not sure yet, so I'll talk to Radoslav about when the end of the semester will be. I think somewhere between 10 days or 2 weeks.
And how many more exercises, homeworks we expect?
So I think that maximum one more apart from this. Probably none. Probably one or one.
Okay. Radoslav told something about lab work, which should be chosen between NLP, RL, something like that. One of them. Do you have some information about that?
Well, that's the first time I hear about this lab work.
Okay, good. Thanks.
Yeah, so that's it for today. If you have any questions, we can discuss them now or on the subject of today's lecture or on the course in general. All right, so then that's it.
Thanks.
See you.
Goodbye. See you.